Hello. We will wait for 5 to 6 minutes and then we will start. Good evening, everyone. So, my name is Abhishek Munshi. I'm a PMRF research scholar at IIT Jodhpur, and I'm your teaching assistant at the course Advanced Power Electronics and Control. This is the week 5. In this week, we will discuss about the types of the chopper and about the isolated DC-DC converters. So, let us wait for 2 minutes, and then we will start about the choppers. After which, we'll discuss about the isolated DC-DC converters. Fine. So, the types of chopper. It's actually there are 5 types of chopper. The type A chopper. Last day I had discussed about the non-isolated DC-DC converter, which are more really related to the types of the chopper. As we see from here, that this is a type A chopper or called as fast quadrant chopper. So it is similar to a buck converter. More or less similar to a buck converter, because at the buck converter after this, which we have a filter circuit, after which at this part we have a filter circuit. If you remember the last class, basically it acts as a step down chopper. Okay, so why it is called a fast quadrant chopper? Because with an, as I said, with an inductive load, if it has, and a freewheeling diode it has here. So what happens when the chopper is on? The supply voltage connected across the load will be, we will find a voltage V, and when it is off, we will not find any voltage, right? So basically, it acts as a, when the voltage is coming, we have a positive type of current because current is flowing through it. So it belongs to this fast quadrant. So we have the fast quadrant chopper. This is the turn on and turn off time of the switch. During the turn on time, the current will rise, and during the turn off time, the current will decrease. This is my output voltage. We'll get the output voltage for that period of time. And the switch current, the switch rise, and when the switch is off, the switch will be zero. Right. Freewheeling diode current. When the switch is zero, the load, if you consider this as an inductive load, it will store some energy and it will fly back through this freewheeling diode, and during that period of time you get the current across this diode. So this is what the step A type A chopper, that is a step down chopper also called. Okay. Next is a type B or second quadrant chopper. So this is basically a step up chopper. So if you see from this image, there will be a time that the, as we discussed on the last class, during there will be turn on and turn off time. During the turn on time, when switch is off, the current will. But here, what happens during the positive half cycle, uh, this diode acts as a reverse bias, right? So during when the positive half cycle, acts as an open circuit. When switch is on, when switch is off, it will act as a forward bias during the negative half cycle, it will flowing through it and store the current. Okay. But what happens to the switch current? The switch current will be since it's the inductive load, it will store the current and energy, and it will bypass through this, right? So that's why you will get this current on the negative half cycle. Okay, so this is just type B or second quadrant chopper. Next is the type C chopper. This is basically a combination of type A and type B. Combination of type. In some book you will find that you will call as class. The combination of type A and type B from the figure it is. Since it is a combination of type A and type B, obviously it will work in the two quadrant. For type A, it will work in the first quadrant. For type B, it will work in the second quadrant. So basically, it works on the two quadrant system. Okay. So during the type A operation, the switch one, the channel one, which is shown over here, that is this is S1, this is suppose S2. So during the type A operation, the S1 switch will on. During the type B operation, the S2 switch is on. Okay. So suppose when the channel 1 is turned off, the energy is stored across the L. Okay. That forces the current to flow through the diode D2. The output voltage on that situation is V0 equal to 0. Okay. But the output current I0 continues to flow in the positive direction, and when my channel 2 is triggered, the voltage E here forces my I0, my load current, in the opposite direction through the inductor and channel 2. Okay. So on turning off this channel 2 or the switch 2, the energy stored in the inductor drives current through the diode. Okay. So on that situation, V0 is equal to V. Thus, the average voltage of this V0 is positive, but the average output current has taken both the positive and negative values. Hence, you can say that this chopper switch A, channel 1 and channel 2 should not be turned on simultaneously. Okay. So this is a class C type of or type C type of chopper which can be used for DC motor control and mainly in the regenerative braking of DC motor. Okay. Next is the type D type of chopper where you can see that there is one channel and one is diode. Okay. So the channels actually the switch, if you call this is a switch one, this is switch two. The switch are connected diagonally. And the diodes are connected diagonally. It's more looking like the asymmetrical topology of the rectifier bridge, right? So here what happens in class D, here also we have two quadrant chopper. It works in this first quadrant and fourth quadrant. Okay. So when both the channel 1 and channel 2 are triggered, the output voltage should be when channel 1 and channel 2 are triggered, the output voltage is V0 equal to V. As you see that this path is completed and the output current flows through the load. Okay, so I naught flows through the load. Now when D1 and D through the load in the same direction, okay, so now D1 and D2 it will flow back through that. When they are on, the inductor which store the energy across L will bypass going back through this diode, and so we will get V0 equal to minus V. Okay. So the average load voltage V0 here also is positive if the chopper turn on is more than that of the off time. Okay, but the average voltage will be negative if turn on is greater than turn off, and if turn on is less than turn off, then average voltage will be negative because more will discharge across the diode, right? So this is a class D type of chopper. So these are the waveforms for the class D for during the positive half cycle. In the negative half cycle, when turn off time is less, then it will be positive as we see from here, because we are getting the voltage across. Since this is my switch is on during the on time mode times, and these are here the switch is on during the on time off less. So that's why the negative half cycle is greater in here. Here the positive half cycle is greater. So appropriately the positive should be more, and here the negative should be more. And next, the class C or fourth quadrant type of chopper. So it can operate on based on the, as you see that when switch 1 is operated, I'm briefly describing here. See when the S1 is on, okay, when S1 is on and S1 S4 basically works as on circuit, so this is on and this is on. So on that period of time, the the current is flowing from the source to the load from the circuit, if you see. So it acts as a fast quadrant. Next case, when my S2 is operated, the S2 and D2 will be on, and S2 when off, then D1 and D4 will conduct. The circuit look like this. Then it will operate in the second quadrant. Similarly, during the third quadrant of operation, what happens? My S3 will be operated, and my S3 and S2 will remain on that period of time. My S2 and D4 will conduct for reverse biasing whenever it will try to discharge through that part. So it will act as the third quadrant. And during fourth quadrant of operation, the S4 is operated, S4 D2 will remain on, and D1, D2, D3 will conduct, right? From here it will conduct. So it will act as fourth quadrant. So basically class C chopper acts as a four quadrant chopper for this reason. Okay. So this is what about the chopper. If you have any doubt in the chopper, you can ask, and we will move on to the isolated converters. Just try to note this down because the circuits are important to solve some problems whenever we'll see some problems. So try to note it down. Fine. Now we are moving into the discussion of the isolated type of converters. So what happens in isolated type of converter? Basically, we have an isolated, we have an isolation transformer between the input and output. We have a isolation by means of a transformer. So in case of the flyback, we use a transformer we called as flyback transformer. So for analysis of this, see when the switch is on, make it when the switch is on, this is the circuit. When the switch is off, this is the circuit. Okay. So basically, we have to assume that the output capacitor is very large. The circuit is operating in a steady state. The duty ratio is D. That is it follows this formula T on plus T off. The switch and the diode are ideal. Okay. So while considering this, we have to calculate. So the flyback converter, if you see the calculations, so during the switch is closed, we see that the equation, you see it. Let me copy this. Mhm. Fine. See, when the switch is closed, that means when the switch is open, then if you apply Kirchhoff's law, then we'll get V1 equal to Vs Lm dt. So on the last lecture, as you said, that can be written as the repel in the inductor by the total time, that is T on time equal to dt. So that will be V1 by Lm. Okay. So on the load side, since it has a transformer ratio of N1 by N2, so it will be N2 by N1 of V1. So it will be V0 minus V2 N2 by N1. Right. Similarly, when the switch is on, my V1 will be minus V0 of N1 N2. And if you solve the equation, it will get the inductor current as this. So combining both of these, we are getting an equation. If I applying the volt second balance during the VL on T on plus VL off T off. So applying the volt second balance, we are getting this as my output voltage relation with the input voltage. So if we have a turns ratio N2 equal to N1 equal to 1, then see the equation is more look like the equation of a buck boost converter, right? So basically, my flyback converter is an isolated buck boost type of converter. Since it's at an isolation, so obviously the turns ratio factor will be added while during calculation of the output voltage. Okay. Now the power absorbed equation will be similar to that of the DC-DC non-isolated converters. The input power will equal to the output power. So Vs Is is equal to V0 square by R. Now the average source current, if you calculate it, it will gives you this value. Okay. So if you have any doubt in the flyback converter, you can ask and try to put down the equations. It will help you to solve the problem. Okay. The try to solve in the manner of the buck boost converter. So it is similar to the buck boost converter. I hope you have all learned down it. Next is a see. So next is a forward converter. So forward converter is basically derived just like the flyback, which is derived from the buck boost topology. The forward converter is derived from the buck topology. See, it acts as a buck converter, right? So if you find out the equation, it acts as a buck converter. So this is a forward converter. This is the isolation transformer. This type of transformer are used in flyback also. The isolation transformer, heavier core. This is the soft core, and they have winding inside it. Okay, and these are the leads. Okay. So the advantages, it is very simplified construction and operation. So it has low input ripple current, and disadvantage is that it requires high transistor rating. It requires active snubbers for resetting the transformer core. It has higher conduction loss, and mostly this type of converter requires transformer which are bigger in size. Okay, but if you see the chargers, mostly the DC to DC chargers basically use isolated type of topology. Most of the charger mostly use flyback. Presently, the Apple and others chargers are made up of LLC type of converter. It's different topology, but mostly they use isolated topology for making the charging circuit. Okay. So this is the forward converter. This is it has an N1, and this is secondary is N2, and there is a tertiary winding N3. So this is the waveforms are similar to that of the buck converter. Okay. Now when the switch is closed, you see that when the switch is closed, it will get a path across this, right? So the current is flowing across this path to this, charge this inductor, and it will couple into the secondary side circuit. And when the switch is open, this inductor gets charged and then is set back to the secondary circuit. But the secondary diode is reverse bias, so we will not get again voltage, but this inductor getting charged, so this will keep charging this capacitor. Okay. So when the switch is closed, you see that V1 is equal to Vs, and we know that V2 has a relation with respect to the turns ratio. So we can write V1 equal to Vs N2 by N1. Okay, fine. Now the input voltage and output voltage can be determined by this relation. So wherefrom we see that the switch current, this is the inductor ripple, mostly similar to that of the buck boost and boost type of converter, the Vs by L. Okay. So if you see, if you calculating, after which if you apply the volt second balance, finally we'll get the equation as V0 equal to dV1. So this is like buck converter. But here's an additional term since it has a turns ratio. So it is V0 equal to Vs d N2 by N1. This additional term is due to the isolation. Okay. So basically forward converter is a buck type of converter. Next is a push-pull type of converter, as we learned from this week. This is a push-pull type of converter. So basically, in push-pull, we have two switch topology. Okay. Here also, when the switch is on, we'll get this switch on, put current, voltage. So when the switch is closed, we are getting double switch, double voltage across this switch too. So from here it can be see that the penetration at the switch in case of push pull converter is twice that of the other converters, right? So if you finalize that this is the inductor ripple during when the switch is closed, we solve this equation. Similarly, when the switch sorry when the switch is closed, we are getting the inductor voltage as this. Now here during this period of time we'll have twice voltage in Vs. Okay. Now when both the switches are open, on that case we'll getting ultimately the output voltage as twice of that of the Vs respect to the Ns by Np is a turns ratio into the duty cycle. Okay, fine. So it is stepping up the converter, so it acts as a boost type of converter, but since it depends upon the duty, so it can be reduced, so it can be a buck boost. Okay. So that is all about the isolated converters. So if you have any doubt, you can ask, and after which we'll solve some sample problems. Try to answer those sample problems. So okay. So if you don't have any doubt, try to solve it. Which type of chopper is used in DC motor speed control? Okay. Try to answer it. Fine, I got an answer. Obviously, Type C chopper, as I said in the Type C chopper, while that it is a combination of Type A and Type B. It can be used for motor speed control and regenerative braking. Okay, fine. Next, in a DC-DC boost converter, the duty ratio is given to regulate the output voltage, which is given as 48 volt. The input voltage is 24 volt. Output power is 120 watt. Frequency switching is 50 kilohertz. So assuming all the components are ideal, what will be the value of the boost inductor? Fine. So if we solve it, see, we know that in case of the boost converter, the output is V in 1 minus D, right? So since D is equal to 1 minus D equal to V in by V0, so D equal to 1 minus 0.5. is 0.5. Our duty is 50%. So, and we know in case of any DC-DC converter, P0 is P0 into I0, which is DC, so we can product it. So that is equal to 120. So I0 will be 120 by my output, that is 24 here. Now we know that delta IL in case of P in by FL. So all the values are given 0.5 into 50 into 10 to the power 3 into so delta IL is I0 if you get this here 5.4. So it is 5.4 by 2 is 2.7. If you solve it, it will be equal to 24 volt. Okay. So 24 micro Henry, the correct answer. Next question, which of the following is the disadvantage of a chopper? Try to answer. So the disadvantage is that high frequency operation can cause EMI issues since it has a isolated transformer over there. It can produce EMI issues. So if have you have to do you have to add a EMI filter before the converter stage, and it has an isolation in between. Okay. Which of the following is incorrect? So this is easy. Try to answer. Class B, Class C is a four quadrant chopper. Is the wrong answer because it is a two quadrant chopper. Class C, two quadrant chopper, which acts as an A and B together. Okay. Next question: in a flyback converter, the inductor of the buck boost converter has been replaced by flyback capacitor, resistor, transformer, transistor. Okay. Obviously, as I said, in case of the flyback transformer, there is a flyback converter, there is a flyback transformer. Okay. Next, for the bidirectional operation of converters, which of the following is correct statement? For bidirectional operation, we need a parallel combination of controllable switch and diode. That means, suppose we have an IGBT and an anti-parallel diode. So this kind of situation, then it will act as a bidirectional. Or if we have a MOSFET, the MOSFET has an in diode, the body diode itself. I discussed in the second lecture or the first lecture, I think. So these are the switches which we can use for bidirectional operation. Next, a step-up chopper has 400 volt DC, 200 volt DC source. Since it is stepping up from 250 to 400, inductor current is continuous and it is on for 20 microseconds. What will be the switching frequency of the chopper? Fine. So if we solve it, so the T off time is given as 20 micro. Okay. So it is 20. So in case of a step up chopper, V is equal to VST by T off 400 into 20 into the minus 6, 250. So it will be 3.2 microsecond. So if you convert it into the frequency, it's 1 by T, we'll get 31.2 kilohertz. So option B is correct. Next, which of the following statement is wrong about a choke converter? Okay, about a choke converter. So choke converter is also a DC-DC type of converter, which is look like this. This is an inductor, switch, capacitor, and diode here. Inductor and other capacitor here. Okay. The choke is also a non-isolated. So here is a load. This is L1. This is my switch. This is C1. This is diode. This is L2. This is C2. So we have an input field, input inductor. So it acts as a boost inductor, and we have a filter just like the buck converter. So basically, choke converter is acts as a buck boost type of converter. The converter is named as choke. So it is choke converter named after the Professor Chook. Okay. So try to answer which of the following is correct regarding this. So this can produce output voltage of same and reverse polarity with respect to the input voltage as it is equal to a buck boost converter. So the statement D is correct. Next, a buck DC-DC converter is given. Calculate the maximum and minimum inductor current. Okay. Try to answer it. I'm giving 5 minutes. Fine, so let me solve it. So here, since it is a buck converter, we know that V0 equal to dV in. So it is 0.4 into 50, that is 20 volt. Fine. You can solve it in two ways. If we solve the delta IL, you can solve it. So it will be 1.5 M, and my I0, since we have output voltage, so my I0 will be V0 by I0, that is 20 by 20, 1 amp. So my I max will be I0 plus delta IL by 2, and IL minimum will be I0 minus delta IL by 2. So 1.75 and 0.25 are the correct answer. You can also solve it by putting this formula directly. Okay. So last question, a flyback converter having the parameters are given. I already solved the equation for flyback. So we have the input voltage 24 volt, output voltage is 5 volt. The turns ratio is also given as 3. What will be the duty? So straightforward. This is the last question. Try to solve it. I'm giving 2-3 minutes. And if you have any doubt in between, you can ask. Otherwise, after solving it, we will close the class. Fine, this is a direct formula, so we derived that for is similar to the buck boost converter, so it is input voltage d by 1 minus d and into by n1, so I have to calculate d. So d will be equal to 1 by v in by v0 n2 by n1 plus 1. So if you put the value, it will be 0.385. So option C is the correct answer. Fine. So if you have any doubt regarding this, you can ask. Otherwise, we'll drop the class here and we'll meet in the next week with a new lecture. So that's all for the day. Okay. Okay, thank you. Okay. Good night, everyone. That's all for the day.